Alright guys, I'm going to make an attempt at solving problem 4.4, like I said I would. So, with no further ado, let's get started. I have the book here off to my side, but you might want to follow along with your own book if you're interested. Start with the loading. We have 25 pounds per square foot. We have from snow load, 10 from roofing and joists, from the deck, and then the joists themselves is an additional 3, and then wires and pipes and that kind of stuff is another 5. So we add this all up, we assume that the whole roof is under 43 pounds per square foot load. So there's our loading. Our next question that we need to know for this kind of thing is, what is the tributary width? So the first thing actually to look for the load on beam 1. So this is kind of awkward. You can see these are the beams here on these spacings. So each beam in the middle here effectively holds this much weight. Well, it'd really be from like the middle here to the middle here on this beam. So that width, if we look at right here, is 40 feet divided by 5. 5 of these little empty spaces. Each beam holds up an empty space, so the tributary width would be 8 feet. For B1. So now we want to know what the actual loading per foot is on the beam. We know that we have 43 pounds per square foot. 8 feet wide would be, let's do a PSF, times 8 feet will equal 344 pounds per foot. I'll write it like this. So notice here we had basically pounds per area, so like pound over length squared times the length, so you get one of those lengths cancels, you have pounds per unit length. So if we have, this one beam, joined here, and it has all this area worth of load on it. This is kind of the tributary width here. This is the 8 feet. And so we look at the loading in this one little 1 foot region here. All this load goes on this part of the beam right here. So that's why we're doing the tributary width, which is 8 feet, times the load per area. So you get 344. Now this is the load on beam 1 from the roof. It also has its own weight, which is given as 15 pounds per foot. Now this is in the problem itself, so you can see, beam 1 and beam 2 are both, where the hell did it go? There it is, 15 pounds per foot. That said, we can do some more adding, and we find out the total loading, 359 pounds per foot. And asks us to draw the free body diagram and show the load conditions for beam 1. So let's do that. I'm kind of going out of order a little bit here, but if I usually prefer when you guys grade, do it like this and all in a row. I'm just trying to write big here. So if we have our beam, it's supported over here by the girders that we'll get to, giving some support load. And there's this uniform load in all my years, I've never gotten better at drawing arrows. It's kind of sad. So I have this uniform load on the beam of 359 pounds per foot. There's your load on the beam. Now the question is, what are the reaction loads? We know that this beam is on the bottom here, 24 feet. That's how long the unsupported length is. It goes from the wall here to the girder. So we can assume that these loads are by symmetry half the total. So if we have call this RA, call this RB, those loads would be 359 times 24 feet. This is pounds per foot. All that over 2. So the reaction load is 4,308 pounds. Both here and here by symmetry. So now let's look at the girders. I'll go ahead and go to a new page for that. I'm going to look at girder G1. Now, in the problem, you can see G1 are these long vertical elements that run up and down here. They act like the walls, but they have these interstitial spacings. So G1 is supported in the middle by columns here and here, and by the walls on either end. So the unsupported length here is 40 feet. So we're going to be looking at something that's 40 feet long. So let's go ahead and draw that now. We'll call this a wall support here. And this is, column support here. These exert the support loads that hold up the girder, G1. Now, G1 has a self-weight of 50 pounds. That's the distributed load on G1. It's not directly holding up the roof, so it does not have that 300-some pounds per square foot that the other B1 did. The way G1 supports the roof is by supporting B1 every 8 feet, which is the tributary width. Let's see, and that is 50 pounds per foot. Right there. Call this RA on this side, RB. Now, what are the actual loads here from the beams? So, each of your beams here has a load that is exerted on the girder of 4,308 pounds. But notice that supports a beam on both sides. So every 8 feet, there is going to be a load of 8,616 pounds every 8 feet. That is 8,616 pounds. There. Let's make sure I don't screw this up. This is 40 feet long. And then we should divide up into, 5 spaces. So I'm not doing too bad here. So there is some question as to, what are the loads right here where there's like a column. Let's call this the column. And what's the load on the wall right here? Make sure that's the wall. Is it going to be the full 8,000 pounds? Will it be half? Will it be nothing? Doesn't matter. Let's start. I'm going to forget those questions here momentarily. So what will it be? If you look here, the last kind of beam in this row is really the wall. So the wall itself, you might consider this as supporting a kind of half tributary width of 4 4 feet wide, whereas the first B1 here has a full tributary width of 8 feet. So if you want to, you can model the load on this girder as the half, which would be 4,308 pounds. So why don't we do that? Load here of 4,308. And on the column here, let's see, we have, full tributary width from that beam right there is holding up the whole thing, but it's supported by the other girder. So we will call this half as well. So 4,308 feet here as well. See, and there would be 4 full beam loads. Okay, that's correct. Okay, I've gone ahead and drawn too small, so I'll draw this bigger. We have load of 4,308, load of 8,616, 8,616, 8,616, 8,616, and 4,308. That's all in addition to 50 pounds per square foot, or 50 pounds per linear foot, my bad. And we have these reaction loads, RB, RA. So now we have to find out what these are. Now notice again here that we actually have a symmetric situation. So if you look at the center here, there's the total number of forces on either side of that are perfectly the same, all in the same spots, except for, this thing which I didn't draw correctly. So it's a symmetric situation, so all we have to do is add up all the forces, divide by 2 to get the reaction loads. So we would have 616 times 4 plus 4,308 times 2 plus 50 times, how long is this? This is 40 feet. This is 45,080 pounds. Divide that by 2 to get your reaction loads. Your reaction load would equal 2,000 or 22,540 pounds. Okay, so there's G1. Now if we want to, we can start with column. We'll call it C1. Just a sec. C1. So this is pretty straightforward. If you look here, this column supports the reaction load from girder 1 times 2. So it's actually just going to be the thing we just calculated of this number. So it has this reaction load here, it supports this, it also supports the next girder here, resting on the same column. So it'd be pretty simple to say 45,080 pounds. Not so bad. Now, let's quickly go through the same process for B2. So B2 is in this little annex of the building here, and it's a little small to see on the camera. But if you notice that over 30 feet, which is the space here, there are 5 gaps of 6 feet. So your tributary width is going to be 6 feet in this case. So your loading will be the 43 pounds per square foot times 6. £258 pounds per foot. And then we would have total length of 16 feet. So here we are, load, oops, dear, of 258 pounds per foot, or 16 feet between the ends here. And I want to know what these reaction loads are. In this case, R is going to be equal to 258 times 16 over 2 equals 2,064 pounds. And pound sign comes across easier. 2,064 pounds here, so that's be 264, 2064. There, that would be your free body diagram for B2. Now, lastly, let's see, I need that sheet of paper. Let's look at girder 2. Let's see here. Girder 2 does the same thing. It basically supports over 30 feet. And then we would have loads every 6 feet. Load here, 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 and here. So these loads will be twice these reaction loads from the columns, or from the beams, excuse me. So that would be 4,128. And then these would be half for the same reasoning we had discussed before, and that, the last little beam here putting on this load is only holding 4 feet of load, whereas the beams in the middle here are holding a whole 8 feet worth of tributary length. 2,064, 2,064. Add this all up and divide by 2 to get our reaction loads, plus the 50 pounds per square foot. So 50 pounds per linear foot, excuse me. So our whole load here would be 4128 times 4 plus 2064 times 2 plus 50 times 30. So this is the whole load, and to get the reaction force, we would divide that by 2. We do that, we get a reaction load of 22,140 pounds. Oh, I'm sorry, half that. That's the total load divided by 2. 11,070 pounds. So this would be 11,070, 070. There. There's your free body diagram for G2, B2, C1. If you want a free body diagram of that, I suppose we can. There. G1, and then the very first one, B1, where we found the total load, found the tributary width, added this self weight of 15 pounds, and then got this. I just realized I didn't add the 15 pounds to B2. So if you put that in, you'd get something slightly more. This would become 260 and change. Then you would bid, slightly more in the end. This might be 2200 or so. So that's how you do these problems. This is fairly similar to the project, so I recommend you take a look, and you'll get started on the project soon. Get started on the project. All right, thanks, guys.